Good evening, everyone. Hello, good evening.
Good evening, sir.
Quite unfortunate that we are still having the same number of people.
Yes, sir.
We would have continued instead of wasting your time. Okay, so I want to say welcome to today's facilitation. This is, today is 17th of April, and we are having our last facilitation for for this semester. So far, we have done quite so many things, and by the special grace of God, we are concluding today, and we are unable to. We'll be able to go through all the topics. By the time we finish today, we would have covered everything that is required of us in Chem 102. Okay, so like I said earlier in the mail I sent, we will go through everything that we are going to do today, and then possibly take one or two tutor-marked assignments, and then take your questions, and then I will wish you good luck. Okay, so let's start without wasting time, because we have got a lot to do today. Okay, so today we are going to be discussing alkynes. So far we have done something on alkanes and alkenes, and today we are looking at alkynes. Alkynes are also known as acetylenes. Okay, and they are called acetylenes because of being derivative of acetylene. Specifically, acetylene is the same thing as ethyne, which is 2-carbon alkyne. And so when you call alkyne as acetylenes, you are looking at them as derivatives of ethyne. Okay, so they are compounds with carbon-to-carbon triple bond. Okay, so when you see here carbon-to-carbon triple bond, you can see here carbon-to-triple bond, you can see here carbon-to-carbon. All these are called alkynes, sorry. In every alkyne, there are 2 pi bonds. There are 2 pi bonds and just 1 sigma bond. If you remember when we discussed the hybridization, when we discussed sp3, sp2, and sp hybridized orbitals, you will recall that in sp hybrid orbitals, which is known for alkynes and then cyanide or nitriles, in that place there was a sidewise overlap of py and py, and then pz and pz. So these 2 different orbitals overlap gives rise to 2 different pi bonds. And that's one is sigma bond formed from formed from sidewise overlap. Remember also that. So what that means is that in alkyne, there are 4 pi electrons and 2 pi bond. I hope that is clear. So their general molecular formula, the general molecular formula for alkyne is CnH2n minus 2. Remember that the general molecular formula for N plus the general for alkene is general molecular formula for alkyne CnH2n minus 2. Their name obtained by replacing the A with YNE. Like you have alkane here, you see, if you remove this, it's alkyne, okay? Like in that is in alkyne, the sorry, I had a little network problem. So as I was saying, let me share the slide. So as I was saying, in alkane have YNE. So you can see this molecule, this is the simplest alkyne, 2 carbon. This is the simplest alkyne, and it is formed from 2 carbon. In 2 carbon alkane, you have ethane. Now you have 2 carbon alkyne, that should be ethyne. So you replace the ANE in ethane with YNE, and then you have ethyne. Then how many carbon do we have here? 1, 2, 3. So 2 carbon alkane, this should have been a propane because it's containing 3 carbon. But here, because of this triple bond, is no longer a propane, it is rather a propyne. Then we move further to this place, we have 1, 2, 3, 4. And then because it is, should have been the name in alkane, the name is now butane. Now, in alkane, just like we have in alkene, there is what is called position isomerism. Position isomerism is where the position of the functional group changes. Okay, isomerism arising from the change of position of the functional group. So if you look at the first one here, which is ethyne, you can see it's just carbon to carbon triple bond. Nothing happens. So there is no other place this triple bond could be. The same thing happens here. If you move it to this place, it's still the same thing. Then, however, from 4 molecule alkyne, if you remove this triple bond here and put it in this place, okay? If you put it this place, you now see that instead of but1-ine, it is now going to be but2-ine, but2-ine, because the position of the functional group have moved from here to this particular position. So just like alkenes, alkynes also undergo positional isomerism. Okay. Just like alkenes, alkynes can as well be terminal or internal. A terminal alkyne is an alkyne whose triple bond is at position 1. So a terminal alkyne is an alkyne whose triple bond is at position 1. while an internal alkyne is an alkyne whose triple bond could be at position 2, position 3, position 4, position 5, and so on, but not position 1. So these are the two major. You can see what we have here as an example. So this is a terminal alkyne. In fact, all of these ones here are terminal alkynes. You can see this is at position 1. This one is also at position 1. This is also at position 1. Then an internal alkyne like this is 1 carbon, 2, 3, 4, 5, 6. So you can see that the triple bond is at carbon number 2. And therefore, this is an internal alkyne. Now, the question is, between internal alkyne and terminal alkyne, is there any difference? Yes, the answer is yes. There is a clear difference because in a terminal alkyne, as we have here, this triple bond is in a carbon that is having a hydrogen. You can look at this hydrogen, okay? So, and the triple bond withdraws electron from this carbon to hydrogen bond. This triple bond withdraws electron from this carbon to hydrogen bond, thereby making this bond weak. And if this bond is weak, then it's going to be acidic, because to break the bond will be easy to donate a proton. And that is why terminal alkynes are usually acidic. Okay, terminal alkynes are usually acidic. So in terms of acidity, terminal alkynes are more acidic than terminal alkenes. And then alkanes actually are not acidic. So let's move on. Preparation. How can we synthesize alkynes? The first method of preparing alkyne, remember, I want you to remember something we discussed last week, and that was on alkene. If we want to prepare an alkene, we can do that by dehydrohalogenation of a halogen alkane. You remember? Do you remember what I'm saying? Hello?
Yes.
Okay. So if you remember that, then it simply shows that if we are going to prepare an alkyne, we just need to have 2 halogens so that we carry on the same dehydrohalogenation. But remember, in alkene, the hydrohalogenation, we had only 1 halogen. But in alkyne, there will now be 2 halogens. So you can see what we have as number 1 here, the hydrohalogenation of dihalide. This dihalide here shows that what you want to prepare is an alkyne. If it's not an alkyne, you remove the di here, and then you just say halogenoalkane, and that will give you an alkene. So, but once you have a dihalide here, what we are preparing is an alkyne. And then you just use a base. This base removes HX, hydrogen halide, 2 molecules of hydrogen halide. And once the 2 molecules of hydrogen halides are removed, then there is formation of 2 pi bonds. And you can see that here in alkyne. The next one we are going to look at is the halogenation of tetrahalides. This one now is no longer the hydrohalogenation. This one is purely dehalogenation of tetrahalides. So this tetrahalides contains 4 halogens. And then zinc, you know zinc is divalent, right? So when you use 2 molecules of zinc, they are going to abstract the 2 halogens so that you have zinc X2. Okay, so, and then the last one is alkylation of ethyne. What happens in alkylation of ethyne is that you already have an alkyne, but that is not the ring, the chain length you want. Maybe you have ethyne or you have propyne, but you want to prepare a butyne or a hexyne. So what you do, you can use the terminal alkyne of lower molecular weight to now prepare more larger molecular weight alkyne. We are going to see typical examples of all of this. So let us take a closer look at what happens in the hydrohalogenation of dihalides. So you can see these dihalides can be of two nature. It can either be vicinal. Vicinal dihalide, you can see what is called vicinal dihalide is when the two halogens are in the adjacent carbon. Okay, you can see this carbon here is having one halogen. The second halogen is on this carbon. That is a vicinal dihalide. So with base, you can remove the halogens and then you have alkyne. R here stands for anything. R could be hydrogen, R could be alkyl group, R could be phenyl group. Then aside vicinal dihalide, there is also geminal dihalide, geminal. So when you talk of geminal dihalide, you are talking of a situation where the two halogens are on the same carbon. You can see the difference. This is a geminal dihalide. This is a vicinal dihalide. Both of them is still, you are still going to use a base, okay? And then you'll be able to get your alkyne. So alkynes from alkene. We can get alkynes from alkene, okay? So how do we do that? First, because this alkene does not have halogen. If it has halogen here or here, we would have just used the hydrohalogenation. Well, because there is no halogen here or here, we are going to first of all introduce a halogen. So this our alkene, we first of all react with a halogen. In the typical case here, we have bromine. Okay, bromine Br2. So when it reacts with bromine in carbon tetrachloride, this is just the solvent. This is just the solvent. So when it reacts with bromine in carbon tetrachloride, you remember halogenation of alkene. Do you still remember halogenation of alkene? We discussed that last week. Do you still remember? Hello, everyone. Hello.
Yes.
Do you still remember halogenation of alkene, which
Hi.
we discussed last?
Yes.
Okay. Okay. So if you remember, then when you add bromine to halogen, you are going to have dihalo, okay, dibromopropane, for instance, because this is propane. Okay. Then this, please, this is not one propane. This is one propene. This Y here should be E. This is not a propane because there is no double triple bond here. Okay, so there will be two bromo groups, okay? And then these two bromo groups will undergo normal dehydrohalogenation. Look at what we discussed earlier. This is the hydrohalogen. So as soon as you brominate alkene, you are getting back this kind of molecule. And then this molecule will now undergo the normal reaction with a base to get you the alkyne. Alkynes from alkanes. If we have alkanes, remember what we discussed on reactions of alkanes, halogenation of alkane, which is done using a HEV, that is a photon or heat or UV, okay? And that usually is giving us using a free radical mechanism. You remember, we mentioned initiation, we mentioned propagation, we mentioned termination. So if you halogenate alkane, you now have a halogeno-alkane. You can see this alkyl halide. Then as soon as you have an alkyl halide, this alkyl halide, when treated with a base, removes halogen and one hydrogen. So there will be double bond at this point. As soon as you have this double bond, what do you do next? You brominate or chlorinate or iodate. you treat with iodine, bromine, or chlorine in way of addition reaction. You can see X2 here, which is addition of a halogen. And then, of course, as soon as you get the dihalo group, you know what to do. You treat with a base, and then you get your alkyne. Then, let us now take a look at the other method, which is dehalogenation of tetrahalides. I remember I just told you that with zinc, tetrahalides will undergo dehalogenation to form zinc halide. So look at what we have here, 1122 tetrabromopropane, 1122 tetrabromopropane. So if you treat this with zinc, okay, this zinc should be 2 molecules, not 1 molecule. If you treat it with 2 molecules of zinc, you are now going to remove the bromide as a zinc bromide. You can see zinc bromide here. Because zinc is divalent, zinc is definitely going to take 2 bromine atom. Okay, so 2 molecules of zinc will pick the 4 bromides. And as soon as that is done, there will be formation of propyne. Take a look at the second example here. Here we are using ethyne. Okay, this is 1122 tetrabromoethane. And then this tetrabromoethane, when reacted with zinc, you can see how the zinc is. We are using this just to show you how the zinc bromide is formed. One is this zinc with the bromide. The second one is this, and then there will be formation of carbon-to-carbon triple bond. The next one, which I said was to elongate the chain, is alkylation of ethyne. Remember I told you something about terminal alkynes being acidic. Because they are acidic, they can now react with base, okay, to form a salt. So this is our ethyne reacting with sodium in ammonia. And then when it reacts with sodium in ammonia, the first thing that forms is sodium ethanide, which is a salt, okay? And then this sodium ethanide, you can see the C here is having negative charge, while the sodium is having a positive charge. And therefore, this can now react with an alkyl halide, okay? The alkyl halide in question here is 1-iodobutane. So the sodium ethanide can react with 1-iodobutane, where this CH2 will now attach this particular carbon. And then the sodium now will react with iodine to form sodium iodide. And that will give us this kind of product, which is 1-hexyne or hex-1-ine. Okay? So remember, because of the presence of this hydrogen here, this molecule can still undergo further alkylation with sodium in ammonia and then halogenoalkane. So this is typical, just an emphasis. Here we used ethyne. Here we are using propyne. You can see in this, there is only one carbon to hydrogen bond that is directly attached to the triple bond. Then sodiumide is a base, okay, which now a strong base, which picks this hydrogen, okay? And then you are now going to have this molecule again. Remember, this and this are the same. The difference is that this is from ethyne, and then this is from propyne. Then as you move further, you can see that this now reacts with methyl bromide or bromomethane, okay? Where the CH3 now attaches to this carbon, and then the Br attaches to sodium, so that we have sodium Br, and then this carbon-to-carbon bond is formed. So, unlike what you had here, where there is still one hydrogen. In this one, there is no other hydrogen that is directly attached to the carbon-to-carbon triple bond. And because of that, this one will not undergo further alkylation, unlike this one that will undergo further alkylation. Acidity of alkynes. I already mentioned it to you that alkynes are more acidic, and this is because of the triple bond, which has higher S character. Okay, so if you look at what we have here, I just wanted to compare the acidity of the various hydrocarbons. pKa, the lower the pKa, the more acidic. Okay, remember when you even the pH 6 is less than pH 1 in terms of acidity. So here we have pKa for alkane to be 49, pKa for alkene to be 44, pKa for alkyne to be 25. So you can see this is more acidic than this, and this is more acidic than that. Reactions of alkyne. Just like I mentioned it to you last time when we were looking at the reactions of alkenes, alkynes will undergo almost all the same reaction with alkene, because in alkene there is carbon-to-carbon double pi bond, one pi bond, while in alkyne there are 2 pi bonds. So alkyne is even going to be more reactive than alkene. So remember when we discussed this reaction, which is hydrohalogenation of alkene, so even alkyne undergo hydrohalogenation. However, instead of one molecule that was consumed by alkene, in alkyne, if you want to carry out full hydrohalogenation, then there must be two molecules. You can see the first molecule gave us an alkene, then the second molecule gave us a halogenoalkane. Now, remember when we mentioned Markovnikov's rule? Markovnikov's rule did not apply in this first one, because the first one we cannot decide because there is no hydrogen. But from this second one, you can see there is hydrogen here, and then there is bromine here. Therefore, the Markovnikov's rule will apply, such that the hydrogen, this hydrogen, will come to this position. You have it here, and then the Br will come to this position. Just like alkenes, alkynes also undergo halogenation. You can see it here. Just like alkenes, alkynes can also undergo hydration. However, there is a difference. In hydration of alkene, you got an alcohol. But in the hydration of alkyne, you first of all get an enol. In here for carbon-to-carbon double bond, all here for OH. And then this enol will now get the most stable tautomer, which is the keto form. So these two are in tautomers. Okay, so this one will undergo tautomerization to give the keto form. So the keto form is the most stable one than this. Then we also remember that boration of alkene gave us alcohol still. So, however, boration of alkyne will still end up giving us a carbonyl. First of all, it will give us an enol, and then this enol will undergo tautomerism to get either an aldehyde or a ketone. The other one is reduction. Okay, alkynes are reduced to either alkene or alkane. It could be reduced to alkene if we use a poison. Okay, this palladium in carbon in the presence of barium sulfate. The barium sulfate here is acting as a poison. Okay, so once you say Lindlar pyridine, then you are definitely ending up with an alkene. However, in the absence of this poison, okay, pyridine, okay, in the absence of the poison, your alkyne will be reduced to alkane. Remember, in the presence of the poison, it was reduced to an alkene. In the absence of the poison, it will be reduced to alkane. What does this poison? It poisons the catalytic property of palladium. It makes the activity of palladium as a catalyst to be reduced so that it won't be able to carry out further hydrogenation of alkane to an alkane. The next one is oxidation reaction. You remember we discussed the reaction of alkene with ozone and then potassium permanganate and osmium tetroxide. So the same thing goes on here. However, in the presence of ozone or potassium permanganate, alkynes are usually converted to carboxylic acids. So we want to look at quickly some of the reactions in detail. This is hydration. We did not look at hydrohalogenation because we already discussed that in detail in alkene, and there is no difference here except for the number of mole of hydrogen halide. The same thing goes for halogenation. So but in hydration of alkene, we usually obtain alcohol. However, hydration of alkyne will give us a carbonyl. You can see it here. So what happens is that this alkyne reacts with water in the presence of a catalyst, and then we now have carbon-to-carbon double bond, OH and carbon here. Okay, remember we mentioned that even this hydration goes through via Markovnikov's rule. So you see how now that there is hydrogen and then there is OH. Then this will now isomerize or tautomerize, okay, to get the keto group, the keto form. So a typical example is a thyme undergoing hydration to give, first of all, ethanol, which is an enol. En here is to account for the carbon-to-carbon double bond. OL here is to account for the OH. And then this enol will tautomerize to ethanol, which is an aldehyde. Then we look at propane. Propane undergoes hydration to give propane. Propane propanone. Hydroboration, which was the same thing as hydration, gave us alcohol as it were with the So the only difference is that here we are having 2 molecules of borane instead of 1 molecule as it were of alkane. So a typical example is this hydroxy 3-hexane. When this is you treat it with borane in the presence of water and hydrogen peroxide, you are going to end up with a hexane 3-one or 3-hexanone. So this is 1, 2, 3, 4, 5, 6. Remember here now, this is a symmetrical alkyne. You can see you can bisect this molecule at this point. You have 1, 1, 2, 2, 3, 3. right? Then if you try to bisect this one, you have 1, 1, 2, 2. So you can see this is not symmetrical. So non-symmetrical alkynes will give you two products. One of the products, the carbon to oxygen double bond will be here. The second one, the carbon to oxygen double bond will be here. So that is exactly what we have here. You see CH3C. So in this one, 2-hexanone, the carbon to oxygen double bond was at this carbon. Then in this second one, the carbonyl group was at this carbon. Reduction of alkynes. Alkynes could be reduced in the presence of Lindlar catalyst, okay, which involves palladium in carbon, activated carbon, in the presence of barium sulfate. This is the hydration itself, the reducing agent here. Okay, you can see this is hydration, addition of hydrogen. So when this hydrogen is added in the presence of Lindlar's catalyst, you are ending up with alkene. Okay, you are ending up with alkene. However, if this hydration reduction takes place in the absence of Lindlar catalyst or in the absence of barium sulfate, you can see you are ending up with an alkane. You are ending up with an alkane. But if there is Lindlar's catalyst, you end up with an alkene, a cis alkane actually. Then the other way you can reduce alkyne is using sodium in liquid ammonia. In the presence of sodium in liquid ammonia, when you hydrolyze, okay, you are going to get an alkene. Now, the basic difference between reduction with sodium in liquid ammonia and reduction with this is that if you are using palladium in carbon to reduce, then you must add a poison if you want an alkene. Otherwise, the presence of this catalyst can make the reaction to give you an alkane. However, if you are going to use sodium in liquid ammonia, you are ending up with a transalkane. There is no way you are going to obtain an alkane with this reagent. But with this reagent, you can get an alkane. Reduction of alkyne continues. We just want to take a look at one particular reaction. You can see 1, 2, 3, 4, 5, 6. This is a terminal, sorry, this is a symmetrical alkyne undergoing reduction first with sodium in ammonia. You can see where we now have trans products, but with Lindlar's catalyst, we have cis products. Remember the difference? This one gives a trans. In trans, the two heavy groups are opposite. In cis, the two heavy groups are on the same side. Ozonolysis of alkynes. Do you remember when we discussed ozonolysis of alkenes? And then we said that we are going to get aldehyde or ketones. But for alkynes, you are going to get dicarbonyl or a carboxylic acid. So this is our alkyne undergoing ozonolysis. As usual, we will get our ozonoid. I want you to take note of this. In the ozonoid from alkene, there is no carbon-to-carbon bond. This bond doesn't exist in the ozonoid obtained from alkene. This bond does not exist. But in the ozonoid from alkyne, you can see there is still a bond connecting the two carbons. And that is why when you hydrolyze the ozonoid, instead of getting two separate products immediately, you are rather going to get this particular 1,2-dicarbonyl compound. Okay? Then, if zinc dust, which is more or less a reducing agent, is used during hydrolysis, that is during this, in this step, if zinc dust is used, then we are going to get only this product. Okay? use zinc dust, let us say hydrogen peroxide. If you use hydrogen peroxide, because there is possibility of breaking this bond, so that this one will form carboxylic acid and this other one will also form another carboxylic acid. Oxidation with MnO4. Just with okay. We are still here. So like I was saying, terminal alkynes, okay, for terminal alkynes like this one, you can see the two products, because when there is breakage of the dicarbonyl here, okay, this other one will just form carbon 4 oxide, while the other part will now form carboxylic acid. That is for terminal alkynes. But for non-terminal alkynes, you form 2 molecules of carboxylic acid. Okay. So use the subtopic of today to play around, and then we will take questions and concerns. The first question there was, how would you react? What are these reactions? Alkyne to a ketone. Convert to one with 2 ohm. How will you do that? Any idea? Hello, John. Hello, John.
Yeah, is it hydration by adding H2O?
Good. Perfect. Perfect. With hydration or hydroboration, any of the two, because you know both hydration and hydroboration of alkyne will give you the same product. So with hydration or hydroboration, you perfect. Okay, so let us take a look at the second one. Second one, who do we still have here? Donald. Hello, Donald. Donald, are you there? Ganiyu. Ganiyu, are you there?
Yes, sir.
So can you help us? How can we move this D? How can we, what do we do to this one so as to get this product? Any idea? Huh?
Hydration.
Hydration. Okay. Let's move on to the next one, number 3. Number 3, we have 1, 2, 3, pen-2-ine. How can we move pen-2-ine to propanoic acid and ethanoic acid. Miriam, are you there? Hello, Miriam.
Hello, sir.
Yes, can you help us with question number C? How we can move alkyne to 2 molecules of carboxylic acid?
Sir, we use oxidation with KMNO4.
Good, perfect. So far, so good. Okay, D. Question number D. John, are you back? Oh, sorry, not John, Donald. Donald, are you there? Donald, are you there? Donald seems not to be with us in flesh. Okay, so who can help us with the way around moving compound D, which is pent 1 in to pent 1 I? Any idea on the steps to get pent 1 I from pent 1 in? Yeah. Daniel.
Yes, sir. Point 1 and from point 1 in. I think it's oxidation.
What to get that product? We give an alkyne. I want to refer you back to the slide where we discussed conversion of or preparation of alkyne from alkene. Okay, somebody saying something.
So it's like we are to convert it first to an alkyl halide, then we treat it with a base, and it will give us an alkyne.
Exactly. First thing is to treat with halogen, maybe bromine, and then we'll now have dihaloalkane. And then the dihaloalkane will now be dehydrohalogenated using a base. And that will give us alkyne. Exactly. Okay. So let's move on. Predict the product of the following reactions of one butene. This is butene reacting with hydrogen bromide, 2 molecules. What will be the product? The product.
Yes, sir.
Are you there?
Yes, sir. I think it's electrophilic addition reaction.
Yes. It's definitely electrophilic addition. So can you tell us the name of the product? Or maybe draw the product and show us. Are you there? Are you done?
Huh?
Huh?
I have idea about the product. I just know it's electrophilic addition reaction.
Okay. Okay. So what happens is this. Remember in hydrohalogenation. In hydrohalogenation, you are adding a hydrogen and a halogen. And because this is a terminal alkyne, you see there is hydrogen here. So it's going to follow Markovnikov's rule. So the first thing that happens is that one hydrogen will come here, and then one bromine will come here. But remember, this is an alkyne, not an alkene. So there are triple bonds. And that is why in the equation you have two molecules. These two molecules means that you are definitely going to add two hydrogens here and then two bromine here. And the product will now be 2,2-dibromobutane. 2,2-dibromobutane. That will be the product. 2,2-dibromobutane. Then, in this one, where we are using Lindlar's catalyst, you can agree with me that, well, Markovnikovs will not come into play because you are adding hydrogen only. It's not hydrogen halide. You are not going to get an alkane, but rather going to put one in or one put in because of this Lindlar catalyst. If there is no Lindlar catalyst, then you are definitely going to get a butane. Because in the absence of Lindlar catalyst, alkynes will now be hydrogenated to alkanes. There is no alkynes will be hydrogenated to alkene. Then for soda alkyne being reacted with this in the presence of this, if you remember in the production, you mentioned alkylation of alkynes, and I mentioned it also that it must be a terminal alkyne. So what happens first is that this sodium remove this hydrogen, okay, and then after this methyl group will now attach, so that we are now going to have 1, 2, 3, 4, 5, 6. Not in, because nothing happened to the triple bond. So the first product here, like I said, is 2,2-dibromobutane. The second product here is 1-butene, and then the third product is hex-3-ine or 3-hexyne. Okay, so let me have your questions, if any. Let me have your questions. Any question? Kani, do you have any question?
Sir, but we need questions, sir. We need questions from you about about the structure. You should ask us about structure, so we should answer. That's what we need, sir.
I should be the one to ask you questions.
Yes, yes.
You want questions from me?
You should ask about. We should name structures.
Eh?
Name structures. You should give us structures. So we should name. We should give the name of the structures.
Are you talking of the structures to the answer?
Yes. You should give us the structure. Then we name. We give name for it.
Okay. Okay. Miriam, do you have any question?
No, sir.
John,
Yes, sir.
any question?
Yes, sir.
Okay. So, Gani, let me assume I understood what you said and then check up on this. Just 1 minute. Let me know if that is what you are saying. You said I should give structures. So I want to know, is it that you want the structures to these answers?
No. Structures to aromatic, acyclic, and cyclic, like that.
So like what he's saying is that, we should have like a class exercise where you give us structures so that we will name it for you.
That was done during our classes on nomenclature now. We are not dealing with nomenclature now. Is it not? That should be our third, either second or third facilitation on 102. That was when we discussed nomenclature, how to draw structure and name, and how to name a drawn structure. We have done that before now. And that was why, if you remember the mail I sent to you about this class today, I said, this should be the last facilitation ordinarily. So, and I was expecting you to come prepared with your questions. Are there structures you have encountered which you cannot name? Then we can look at it together and provide the name. Are there names that you cannot generate the structure? Then we can look at it together. Today's facilitation had nothing to do with nomenclature. We were strictly discussing alkynes, except maybe if you are having personal problem on that, I would want you to go back to the video of maybe week third week or second week or fourth week. Just find out which of them discussed nomenclature and then quickly go through it. If there is any problem, you have my email address. Okay, you can send me email, sir. Okay, we have done, because I think the major problem is that a good number of you have not even had time to read the lecture material. Okay, so even if I say let us have because usually when time permits, I usually have maybe just 1 hour after the normal facilitation. When we will now interact, by then you must have gone through everything, and then you bring questions that you were not able to attempt. Okay, so I want you to first of all look at those things, except you want us to just take a look at the ones here which are not many,
sir,
as far as momentum.
Sir,
yeah?
I don't know if this would be too much of a stress on you, but chemistry is a bit of a complicated course or subject. So I don't know if it's going to be too much for you. Can you just drop some kind of like mock questions for us to attempt, like through the email? I'm the one that sent you an email this afternoon for the slides. And
Okay,
you told
the
me
PowerPoint.
Yeah, you told me you would send all of them. So I don't know. Can you add that together with the slide you're sending? Maybe just some more questions, just to get us prepared for the exam. Since you said this is the last lecture we're having, just something, maybe 20, 30 questions, just to keep us.
I get what you are saying.
Yeah.
I understand. So let me first of all confirm that all of you used to get emails from me.
Not on my school email. That's why I sent you an email with my personal email.
But the mails I sent on your school email, do you get them at all?
I didn't see anything. Maybe I have to check again. I didn't get any notifications.
Okay. Gani?
Yes, same here, sir.
Do you receive my mail from the university?
No.
You don't receive my mail from the university.
Yes, I usually go to the TME. So I copied your link, and then I put it on my browser. Then it will link me with the class. So I don't normally receive your mail.
Okay. So, well, you know, let me tell you people one thing that is going to help us better. You know, in National Open University, they really believe that the student has got a lot of work to do on his own. I hope you are aware. Are you aware of this?
Yes, sir.
Good. So if you look at the course material for Chem 102, from the beginning, there are lots of questions. After each section, there are questions. You understand? So what I was expecting is that after reading and then after attending the facilitation, there are still questions you were not able to answer. Because by the time you finish those questions on the course material, you must have covered whatever any person is going to ask you in an exam. That is the truth. Are you getting what I'm saying?
Yes, sir. Yes, sir.
So what I advise we do is to take a little time and go through the material, okay, and see if there are questions we were not able to attend, okay, but we have to be fast before the exam, so that if there are such questions, you can just send me a mail, right, sir, that we want maybe an hour so that we discuss those questions. I will give it to you. Are you with me?
Okay, if a single person has those questions, then how do we connect with others to also come online to?
If the single person contacts me, I believe that person should, and I agree. Why am I say let's move by the guarantee that by next week Monday all of you have gone through the material? It doesn't really make sense. Are you there?
Yes,
I don't know
sir.
if you are getting what I'm saying.
Yes, sir.
So I would want a situation, okay, let's say in the next 2 weeks. Do you have the timetable already? No. Is the examination timetable out?
No, sir. No.
Okay, so should I now give you the mandate of going through the course material and even the PowerPoints in 2 weeks' time, so that this time next 2 weeks we can now have 1 hour to see the questions we were not able to answer? Is it okay by you?
Yes, sir. Yes, sir.
Okay, so we are tentatively going to have a class 2 weeks today, Monday, the same time, to answer questions. That one is not facilitation. That one is, I will just sit down, connect with you, you will ask question, and I will address that. I hope it's okay.
Yes, sir.
Is that okay?
But concerning the message, are we to go to the TMA portal, or will you email us? Will you send the link to us on our mail, on our school mail? So
Which link? You mean the link for the scheduled class?
Yes, yes, sir.
No, you are going to use the normal link for these our normal classes.
Okay, sir. Okay, sir. Yes, sir.
We are going to use our normal link.
Okay, sir.
All right. So I'll be waiting for you. Make sure you have loads of questions that day.
Okay, sir.
All right.